All right, Faye, go ahead. You are muted.
I can't share a screen right now.
Oh, sorry.
Yeah.
Okay, done.
Hi, Bei. There's a question before the class.
Yeah.
So I think we have scheduled a meeting today with Sarah, but I didn't remember when. Like you didn't send a confirmation email to us.
Let's talk about that after class.
Okay, sure.
Okay, can you see my screen?
Yeah.
Okay, so I'm gonna do a simple demo. So here, let's say if I have my data right here and I kind of want to see, first of all, I really want to see how it looks like. And then let's just go plot it. And then I'll get something like this. So you can see that we have a flamingo here. It's a little hard to turn it around, but here's kind of the structure, right? You have the head and then you have the two legs at the bottom, and then here's the body. And then if you kind of make it larger, you can see that the body is kind of like a little bit more like sparser than the rest of it. So, okay, so now let's run, let's look at Kepler Mapper. So here is how you would set it up. So after you install Kepler Mapper from the instructions, it's very easy. What you would do is you come here and then you set up the mapper, and verbose just tells you that they will give you a lot more information on the final result. So it would actually show you the different parameters on the screen. And then here you choose the lens, which is the filter function. Here I'm just doing a very simple, I'm doing a 1D mapper. So what this actually does is it sums up the three coordinates, so X, Y, and Z, and then do some scaling. So this is a 1D mapper. And then after that, you set the parameters down here. So here's the filter. And then here you have, I'm using dbScan as the clustering algorithm. And then here you set the dbScans, epsilon, and minimum sample size. And after that, you set up the cover. And then here you have the cover size. Here, because it's just a 1D mapper, so it's just the interval. And then you have the percentage overlap, which is 0.4 that I'm set it up here. And then after that, you just do visualize, and then it generates a HTML file that you can just view on your browser. So let's do that. So this doesn't, it's not like interactive. So Mapper Interactive gives us a lot more freedom to kind of play with the software, but this doesn't do that as much. So this, I'm just converting it into a matplotlib graph instead of the mapper graph. So you can kind of see already the structure of the flamingo. So let's look at the mapper. So I saved it in output, and here is test 2, and then let's open it up in Chrome. So this is the force-directed layout. Let's kind of drag it out a little bit. So here, so can you see that already the structure? So here's the head right here, and then we have the legs down here. So you can click on these and then you can see what happens inside. So like here you can see all the parameters that you set. So here it tells you, so this is like the very simple filter function that I use, which is the sum. You can't see it here, but this is the, oh, here you can see projection sum. And then the scalar is the min-max scalar, which is the very simple filter function. And then down here, you can see the node distribution. So this tells you like, so it splits up the node values based on the filter function from the lowest to the highest, and then you can you can kind of hover on top of each node, and on the left you can see the cluster members. So here you can see that most of the nodes in these clusters have high values right here, and then there are a few with low values. Yeah, so there is, I think, so this is a very simple data set. Kepler Mapper has a tutorial. Actually, why is it not letting me? Kepler Mapper have a tutorial that has more. So someone asked yesterday, what's a good filter function? I think Kepler Mapper has a tutorial on like a much more interesting data set on the cancer data set. And then they use like two different filter functions. So you have lens 1 and lens 2 right here. And then they actually explain, there's a note at the end that kind of tells you why they chose these filter functions. So a note on the choice of filter function. So, you know, like some of these are based on prior knowledge and some of them are kind of like just doing it based on the geometry, but that's kind of how you would choose filter functions. If you want to dive more into more complicated data sets, you can look at this tutorial right here. I'll put it in the chat.
All right, cool. Thanks, Faye. So yeah, so we just want to get a sense of a different type of software for computing mapper. The major differences, as what you see, is that Kepler Mapper is designed for someone sort of with some coding background and sort of going into sort of specify the parameters. It has some interactivities. Actually, once you load up the HTML file, you can kind of look at what the memberships are for each node of the mapper graph, and there's some histogram and distributions of it. But the major difference is that compare that with, say, Mapper Interactive, is that Mapper Interactive is actually computing all the mapper graph on the fly as you're adjusting the parameters, versus the current framework that Faye has showed is that each time you, for Kepler Mapper, at least the default setting, you have to specify sort of the specific parameter you want, then you generate the particular mapper graph at that setting of parameter, and you can kind of play with that fixed thing. So, and, you know, but also, in some sense that it had its sort of strengths and it has its weakness, but it's also supported with sort of Python, so you can actually, you know, kind of play with the code as well. Same thing with Mapper Interactive, where you can go to the source code and you can modify it. But Mapper Interactive was also designed for users who might not even have any programming background, so you can still use the interactive interface to play with the data. But I would like to kind of include this because this is one of those, you know, a few years back, before we have Mapper Interactive, this is sort of my go-to tool for folks to want to learn the mapper construction. All right, so today my second agenda is I'm going to go back and to compute persistent homology. We kind of did that last time for a few examples. We're going to do one or two more examples today, just to get a sense of what am I doing when I'm computing persistent homology. And then if I have time, I'm going to go back to the mathematical formulation of it. I kind of intentionally did this, that, you know, I'm going to show you how the algorithm works to compute persistent homology before I show you the mathematical formulation of it, because then, you know, you are not intimidated by the math part of it, but much rather to say, hey, it's actually quite simple for me to compute persistent homology. Even for small data set, I can do it by hand. All right, so that's what I'm going to do. Okay, so what I'm hoping we can do is try to do it together for a few more examples. And if you want, you can suggest an example and we can do that together with the whole class, okay? So remember last time what we did this simple example. It's 3 vertices and 3 edges. There's no triangle in the middle, right? So there's a tunnel and we see the barcode, the corresponding barcode of what you get. Now, what I would like to do is move on to the next example, which is slightly more complicated. In this particular example, you see that I have, you know, I basically have 2 triangles and they are all filled, okay? So you expect that as I go through my, what I call filtration, which is basically the ordering of my simplices, that I would expect to see at some point, I'm going to see a birth of a tunnel and the depth of the tunnel, okay? So we are going to expect to see some dimension 1 homology as I go along, okay? So here is the same before, where my number is both a label of the simplex, but also the time it appear in my sort of evolution or my filtration. So in this case, what this column of my boundary matrix is doing is to say that, well, my vertex 1 shows up first, then my vertex 2, then my vertex 3, then my vertex 4, then the edge 5, edge 6, edge 7, edge 8, edge 9, and then the triangle 10 and triangle 11. So that is the ordering of the simplicities showing up. Okay. And now remember the boundary matrix is that the boundary of an edge, it's vertex. So the boundary of edge 5 is vertex 1, 2 that corresponding to those two ones. And then the boundary, say, of edge 7 is vertex 1 and vertex 4. So vertex 1 and vertex 4. And then because this filtration, I have appearances of triangles, right? So the triangle 10 has a boundary, the immediate boundary of a triangle are its edges. So I have the boundary of triangle 10 is edge 5, edge 7, and edge 8. So what do I look at? So basically I have the boundary of this triangle here is the edge 5, edge 8, and edge 7, okay? So that's how I construct this whole boundary matrix. So now what's going to happen is that I'm going to do the reduction as I did before. So let's recall the reduction frame, okay? The reduction is that I start with, I'm looking at column by column. If the column is empty, I ignore it. So the first column that is non-empty is a column corresponding to edge 5. And I'm going to start looking at this column and look at the lowest one, okay? So lowest one is this one. Again, I look to the left. There's nothing I need to do because it's completely 0 to the left of it, okay? Now I look at the next column, non-empty. I look at the lowest one, okay? I look to the left, complete empty, nothing I need to do. Same thing with the 7th column, lowest one, complete empty to the left. Okay. Now the next step is where things become interesting. I'm starting with column 8. Now, if I have column 8, I'm going to look at the lowest one. The lowest one, if I look to the left, I see a column that already have a 1. So there's something obstruct its view, if you want to imagine that. So then what I need to do is I'm going to add the current, I'm going to add this column 7 to column 8. So I'm going to add 7 to 8. I'm going to put an arrow, but also I'm going to label this column to say 7 plus. So when I add 7 to 8, right, I'm going to add essentially, I'm adding 1 to 0, 0 to 1, 0 to 0, 1 to 1. Okay, so I get 1, 1, 0, 1 plus 1, which is 0. Okay, so again, let me simplify a little bit. Once I add to it, I get the new column to be 1 and 1 and 0 and 0. That's what I get. So now, based on this new column, I'm not done yet. Oops. Okay. Hopefully that's last my thing. Otherwise, I'm going to be, hold on. Hopefully I go back up. Okay. So now what I have is I have a lowest one again for this column. And I look to the left. Okay. And is there any lowest one that, so, okay, so I'll be a little bit careful. When I say I'm looking to the left, I'm looking for the lowest one that is conflicting with me, okay? So the lowest one that is conflicting with me is coming from column 5. So what I'm going to do is I'm going to add column 5. I'm going to add column 5 to this, okay? So now if I add column 5, all the ones cancel out. So now I have 0 out this entire column, okay? Okay, now let's move on. I'm going to do, I'm going to do column 9, okay? When I do column 9, I have the lowest one, okay? And I look to the left, there's the lowest one from column 7. So 7 is add to 9. Okay. So when I add 7 to 9, I have again 1, 0, 1, 0. Okay. Now the next thing I need to do is I look at to the left of the lowest one to column 9. The lowest one, there's another lowest one from column 6. So I need to add 6 to it. Okay. So now if I add column 6 to it, 1, this become 1, and this canceled out. So now column 9 is just 1 and 1 on the very top. And I look to the left again, there's a column with the lowest one that's conflicting with it. That's 5. So you add 5 to it. So basically I add column 5, 6, 7, all to column 9. The end result of it is, we know that all of it is going to cancel out. So column 9 is now completely 0. Okay. So now let's look at the 10th column. Remember the 10th column now is triangles. Okay. So with triangles, I'm still going to do exactly the same process. I'm going to look at lowest one. It's right here. Nothing to the left. I'm good. And lowest one of the next column, nothing to the left. I am good. So now I have finished my reduction process, and I'm going to try to read my persistent barcode from this. Okay. So let's do the process where I'm going to look at the birth time first, okay? So the birth time, meaning that I'm looking at the birth of a feature by looking at all the empty column. So all the empty column here is the first column, second column, third and fourth. And this column, the 8th column after reduction, the 9th column after reduction. So you know that there is a feature born at time 1, 2, 3, 4, 8, and 9. Okay, so all these are sort of birth time of my features. Now, some of them disappear or dies, some of them live forever. So let's look at what are the ones that sort of disappears in a finite time. I'm looking at the lowest ones in those, lowest one that is enclosed by those rectangles or squares. So if I look at the first one, it says there's a feature that is born at time 2 and dies at time 5. Okay, so there's a feature born at time 2, dies at time 5. That's my first bar. The second bar is there's something born at 3, dies at 6. The third one is something born at 4, dies at 7. And then there's something born at time 8 and dies at 10. And something born at time 9 dies at 11. And then the one that born at 1 never dies. This corresponding to the sort of the component that never disappear during this filtration. So what's going to happen, that's exactly what you see. There is, among all those barcode, the 0-dimensional barcode are 1 to infinity, 2, 5, 3, 6, 4, 7. And then dimension 1, which are the born and death of tunnel, 8, 10, and 9, 11. Okay, and that's what you get. All right, any questions for this example?
There's a question in the chat. Do we do carry on the first row? Oh no, wait.
What does that mean?
Ray, can you unmute yourself?
Yeah, so basically like, do we need to like even carry the digit like the 1 + 1? Do we still need to represent it in some different way, or we just keep it in the first row as it is?
If it's 1 + 1 is 0, so we just replace it by 0.
Okay, so we don't need to do any special things after that.
No, because remember our arithmetic is Z2 coefficient, right? 0 + 0 is 0, 0 + 1 is 1, and then 1 + 1 is 0. Right? But one thing that I did not tell you is that we do record this part if you want to. If you look at the persistent implementation, some of the algorithms or implementations don't keep track of this. But this is actually quite interesting because what is this saying? 5 + 7 + 8. 5 + 7 + 8. This is what? My one-dimensional chain. I'm saying that this column, there's a loop born at time 8. Why? That loop is described by 5 plus 7 plus 8, right? That tunnel is enclosed by this linear combination of edges. The second loop that is born, or in some sense represented by this generator, is 5 plus 6 plus 7 plus 8, right? Which is a nice column after reduction. What is that looks like? It's 5 plus 6 plus 7, plus 9. That's another generator. So those sort of the labeling of how which column is added to it, the corresponding label of that column, tells me in this particular reduction order which linear combination of edges give rise to the birth of that tunnel. Okay, that's what's interesting. Okay, so what's next thing that is hidden in this matrix reduction process is, remember I said there is a tunnel born at 8, dies at 10. What does that mean? A tunnel born at 8 is when I have the edge 5, 7, 8 shows up in my filtration. And it dies when the triangle comes in. The triangle kind of fill it in, right? So that's why that tunnel disappears. Then the second tunnel is when the edge 5, 6, 7, 9, it described at the time of a birth of a tunnel. But remember, the 10 already come in to destroy half of this tunnel, but the other half is still there, described still by this linear combination. Then when the triangle 11 shows up, it destroyed this tunnel. So that's why you have a tunnel that is born at 9 and disappear at 11. Okay, so again, if we want to understand this more detail, let's just do this here. You know, again, let me just repeat this. 1, 2, 4, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, this is my filtration. And let's just do it step by step. I have, remember my barcode. Let me just repeat this thing here. Copy. Okay, so this is my barcode, okay? But without the matrix reduction, you know, since this example is so simple, you can actually go through this, you know, kind of just go through this by a filtration, and we'll define filtration mathematically, but it's just an ordering of simplices showing up in as I change my parameter. So ordering, vertex 1 shows up, vertex 2 shows up, vertex 3 shows up, and vertex 4 shows up. What did this all correspond to? They all correspond to the birth time of a component, 1, 2, 3, 4. Okay. Now the first edge 5 shows up. It connects the two component 1, 2 together. So it's destroyed the younger component. Remember, younger one dies first. So the component 2 dies first. So it's corresponding to, oops, it's corresponding to a component that's born at 2 and die at 5. So that's corresponding to this bar right here. Now the edge 6 shows up. So the component now represented by 1 merged with the component 3. And 3 is a younger one, so 3 dies. So that corresponding to the bar that's born at 3 and dies at 6. 7 shows up, and when 7 shows up, it merges a component represented by 1 versus a component represented by 4. 4 is a younger one, so 4 dies. So there is a component, there's a birth and death of 4 versus 7. So that's a birth and death of a component. Now, any further addition to this simplicial complex does not change the number of connect component. The more interesting thing happen now is a tunnel. So if I add the edge 8, I see a tunnel right here. Okay, so that corresponds to the birth of a tunnel. Now, if I add edge 9, that gives rise to another tunnel. Okay, And visually, you see the tunnel is actually enclosed by the edge 8, 6, and 9. However, based on the reduction, this same tunnel can also be represented as 5, 6, 7, 9. But let's just look at what is happening to the space. The moment I add 9, my space basically, this is where I add 9. So now you have 2 tunnels. Okay. Now, when I add the triangle 10 is the next step. If I add this triangle 10 in here, that is my triangle 10, it's destroyed the first tunnel that's created, but the second tunnel is still there. And when I add the triangle 11, sorry, let me just, when I add the triangle 11, that's when the second tunnel is disappeared. Okay, and that's your barcode. Okay, so we just validate my computation is correct, that even from this intuitive understanding of when component appear, disappear, when does a tunnel appear or disappear, that's exactly what I get out of this matrix reduction. Okay, but what's interesting about it is I want to give one more example of the following simplicial complex. It looks exactly the same as before in terms of the shape of it. The only exception is I change the ordering of when does simplices show up. So again, let's look at it. I will say vertex 1 show up, vertex 2, vertex 3, vertex 4, and then edge 5 that connect 1 and 2, edge 6 connect 1 and 4, edge 7 connect 2 and 4, 8 connect 3 and 4, 9 connect 2, 3, and then the triangle 10 and triangle 11, okay? So it's just a small perturbation of the ordering of what we have before. And correspondingly, I have my matrix, okay? So I can now do the same kind of reduction again. Well, starting from my matrix, boundary matrix, lowest one for the 5th column, lowest one for the 6th column. Now, when I'm at the 7th column, I'm going to look at the lowest one. Well, if I look to the left, there's already a lowest one that is conflicting with it. So I'm going to add 6 column to 7. So I add 6 to this column. So when I add them, 1 and 1 cancel out. I got 1, 1. Okay, so I basically have this one cancel out. Then this column has 1, 1. The lowest one again is 1. So it's on the second row, okay? And then that conflict with the 5th row, which the lowest one of the 5th row. So I add 5th row to it. So now if I add to it, you know that we're going to cancel everything out. Okay, so that's what you get looking like this. Now, if I start with the 8th row, I look at the lowest one again. It's going to conflict with the 6th row, so I add 6 to it. When I add 6 to it, I get something looking like this. And now if I look at the lowest one, I'm good, right? There's nothing conflicting. So that's why this column has an end result looking like this. And the 9th row, again, if I look to the left, okay? If I look to the left, it's conflicting to the 8th column. So I'm going to add 8 to it, okay? And now the 8th column is 1, 1, 1, and 1, okay? So now it's conflict, the lowest one is conflicting with the 5th column, so I add 5 to it, and everything cancel out. Okay, so again, nothing conflicting with my columns associated with my triangles. Now I'm going to read off from this, okay? I'm going to, again, looking at the burst time. The burst time are features are empty columns. So 1st, 2nd, 3rd, 4th, 7th, and 9th. Those are the burst time of my feature. Now I'm going to look at the lowest one. So I will have a feature born at 2, disappear in 5. So a feature born at 4, disappear in 6. And a feature born at 3 and dies at 8. Oh, wait, actually, I just made a mistake. So this is 4 times 6. So 6. 3 times 8. Right? 3 times 8. And then there is a feature born at 7 and disappear in 10. And 9 versus 11. Okay. Among them, okay, of course, this one born at 1 never dies. Among them, the yellow ones corresponding to 0-dimensional features. And the pink one corresponding to 1-dimensional feature. All right. So again, let's look at the ordering of it. There is a feature that's born at 7 and dies at 10. So what does that mean? When 7 shows up, it looks like, so when 7 shows up, it's this edge, and it disappeared. Well, when 7 shows up, and it disappeared when it got filled in. Okay, so you know that you have a tunnel that is born at 7 and dies at 10. And you know you have another tunnel that is born at 9 and dies at 11. So one thing that I haven't emphasized is that when you look at a barcode, the death time minus the birth time is how persistent it is. It basically means how significant this particular feature is. The bigger it is, it means the longer it has lasted. And then in a lot of applications, not all the applications, a lot of applications, it means it's a more important feature. So in this particular case, what we see is that, if I'm looking at the persistence value, the first bar, which is born at 1 and never dies, has an infinite persistence. What did this mean? This means it's a very important feature because as I go through this filtration, this component never dies. So my space always have one component. Okay, so this is a very significant feature. But it's also in a lot of data analysis is the least important feature for data analysis tasks because no matter what data you have, ultimately you're always getting this one component. So it's not very good at using it to differentiate space from space. Okay. Now, the next one is born at 2 and dies at 5. It has a persistence of 3. The next one, born at 3 and dies at 8, has a persistence of 5. And this one has a persistence of 2, right? So it's corresponding to how long does this component last? There's a component that's born at times 4 and dies at times 6. So its persistence is 2, meaning that it's kind of lasted two time steps in my filtration. Now the loop is interesting. I have a loop that is born at 7 or a tunnel born at 7 and dies at 10. So it's a persistence of 7 and then the other one has a persistence of 2. If I want to compare this with a previous filtration, so I designed those intentionally, the previous filtration, remember I have a tunnel that is born at 8 and dies at 10 and another tunnel born at 9 and dies at 11. So this one has a persistence of 2, and this one has a persistence also of 2, compared to the next example where there's a persistence of 3 and 2. So what did this mean? This means that depends on how my filtration is designed, which is when is my simplices show up in my filtration, is influence somewhat a measurement of how important my features are. So if we look at the barcode of those two space, example 2 versus example 3, they actually have a different signature, right? It's because of how the simplices shows up. Okay, any questions? All right, okay, if there's no questions, my next goal today is now we went through some example by hand. Let's go back to Ripser and see what Ripser does. Okay.
Okay, should we take a break?
Yes. Okay, let's take 5 minutes break. So you can try to install Ripser, and we're going to go through a few synthetic examples. Okay. And feel free to ask questions if you have any.
Do I need to install Ripser to follow along now?
You can. I mean, it's the installation is really just a few lines. Yeah. So actually, I have the slides. If you just go to Ripser, you just clone it, and then yeah, you're good from there.
If you have a Windows machine, it could take a little bit longer.
Yeah. But what you can do actually is Faye, I wonder, I'm hoping I can attach a file here. Just a second. Let's see if I can chat. When I chat, can I attach files?
Yes, you can just click on file and then.
Perfect. Okay, so I'm going to attach some files for people to play with. So people don't have a Windows machine, they can do the online version of Ripser. So
the Python package also works for this project.
Yeah.
And that one is much easier to install than trying to install C++ on a Windows machine.
Mm-hmm. All right, I'm trying to attach file. Okay, so chat, attach file. Computer, okay. As long as folks trust what I'm posting here. Let's see. I'm going to post simple example. I'm going to post a cube. And I'm going to post a square. I'm going to post a triangle. Okay. Yeah, I think I have this example here, which is a square. I have example here, which is the triangle. Yeah, an example here, which is a cube. Oh, actually, there's a different cube. Wait, I have two different cubes. Cube 1, cube 2. Let me do a cube 2.
I have one question.
Yeah, go ahead.
So now I only have an intuition of how to compute persistent homology, but is there any formal expression of the algorithm, like a pseudocode or something?
Yeah, so it's actually described in the textbook.
I see.
But we're going to go through some mathematical formulation of it. It's basically boiled down to a matrix
Column reduction?
Yeah, it's basically a formulation of decomposition of matrices.
I see. So
yeah,
I have a
so that's why it's
concern
interesting. Sorry, go ahead.
Okay, I have a concern here is that when you're doing the boundary operator, we are not considering the ordering.
Yeah, the ordering doesn't matter actually.
So do we do that in the formal?
Sorry, not say ordering doesn't matter. Depends on what you mean by ordering. How do I add? Like which one do I add first? Matters somewhat. So it's going to change the end result of so when I talk about the ordering now, I mean like how I'm adding the columns to the current column, and that made effect of my final generator representation, but it does not affect, if I have a fixed filtration, it does not affect my barcode.
Okay.
Yeah, that's what I mean. So Faye, when do we take a break? Is that the current break?
Yeah, I think we're about done.
Okay.
I have a quick question, Dr. Wong.
Yeah, go ahead.
Yeah, so let's say talking about that topic, if an edge spawns two triangles, is it typical just to spawn first, so to say, the one that comes like lexicographically first?
Well, what do you mean by that?
Yeah, so if an edge spawns two triangles at the same time, like if two triangles are missing the same edge, it doesn't matter which one you pick to spawn first, since they spawn at the same time parameter.
Oh, yeah. So then it's an arbitrary choice.
Okay, but the ordering in which you pick, do you have to stay consistent with that ordering, or it really doesn't matter when you come up with the same problem later on?
Right. It does not change because they show up at exactly the same time. So it does not affect your barcode.
Mm-hmm.
So that would be my answer. It will not affect your barcode.
Okay, fair.
Yeah. Okay, so let's do this. Okay, so I would like you to go to this website, Ripser website. I also want to go. Actually, I should do that on my side too. So GitHub, Ripser. Okay, and then there's sort of an online version. Let's do the so the first thing we do is you do this. If you go to the web page, so I'm going to put it in the chat. Okay, hold on one sec. Trying to figure out where my chat window is. So this is a GitHub page in the chat. So what you want to do is to try to kind of clone it on your machine. Of course, this instruction is for Mac and Linux machine, and I'm going to share a different screen. Stop sharing. Share. Okay, so now I'm sharing my desktop. Okay, so this is what, I already have it set up. If you haven't, then you follow the instructions here. You just do a git clone and you go to the Ripser page and then you do make, right? Of course, it's assuming you already have a compiler, a C++ compiler that's already there, which I do. So now I'm in the folder. I'm in the Ripser folder, okay? And now I would like to do an example. Okay, I'm going to use the same example as what they have. I think I have it, okay? So what it does is that this particular data set is provided by default is a distance matrix, okay? So what's interesting about it is Ripser is based on Rips filtration. So remember Rips filtration or Rips complex or Viatorius Rips complex is constructed based on pairwise distances between points. As I'm increasing my parameter, which is a radius parameter, when the radius parameter reach a certain threshold where the ball of that radius touch each other, that's when an edge is going to show up. So if you just provide the entire just pairwise distance matrix, that's enough for it to construct a Rips filtration. So what did that mean, right? Remember, Rips filtration is that when there is a pairwise edge shows up for a triangle, the triangle shows up without checking three-way intersection. That's what Rips filtration is. So what Ripser does is that it says, okay, there is a distance matrix that I provide, and it's come from 192 points, and then it use some sort of threshold to stop the filtration. So I only go up to a radius of this much, okay? And then it's going to return what is the dimension 0 barcode. And the dimension 0 barcode is, all of them, remember this coming from a point cloud. So all the points in this point cloud shows up at time 0. And then the second part is basically the radius at which it merges with the nearby component, okay? So all this corresponding to the 0-dimensional bar. And I could tell you there is exactly 100, if there's 192 points, how many 0-dimensional bars do you get?
$192, right?
Exactly, because every single point gives rise to a component. And then there's an infinite one because that's a global component that never dies, okay? So if you go down, see this is an infinite one that never dies. And everybody else at some point is going to merge into one giant component, okay? And, you know, I'm going to mention it now, and we're going to visit that later. It turns out if you have a point cloud, the radius at which they merge, if you actually just connect those points the time they merge into a component, you are basically looking at a minimum spanning tree of those points, because the minimum spanning tree is sort of the minimum cost tree that connect all the points. And that's exactly also how component emerged, is based on that minimum spanning tree. But minimum spanning tree is not unique. That goes back to, I think, David's question, is that, you know, like the minimum, the way how, you know, if you're giving a sort of a bunch of points, depends on how distances are distributed. You may have a unique minimum spanning tree, or you may not have a unique minimum spanning tree, which is, if you don't have a unique minimum spanning tree, that's when those sort of barcode sort of change. Sorry, the barcode doesn't really change, but the structure of minimum spanning tree will change. All right, so now you are looking at dimension 1 barcode, right? So again, what's happening is now you have to imagine our earlier lecture when we had talking about sensor data, right? I'm constructing Ripser complexes out of a bunch of sensors, and at some radius parameter, this is where the boundary of a triangle shows up, okay? And then there's times where those sort of a boundary triangle shows up, but then there's also bigger loops that shows up, or big tunnels that shows up, and this is exactly where tunnels are born and die in this process. Okay, so there's a bunch of, you know, one-dimensional features too. Okay, so now if I do the same thing, except that what I want to do is I want to do my cube data, which I just you know, I just put it in the chat if you want to play with it. And then the cube data is very simple. The cube data, or maybe let's start with a square. The square data is just, there's 4 points. 1 point at the origin, and then there's 2 points, 0, 1, 1, 1, 1, 0. That is your square, okay? So now I want to say, what is a Ripser simplex do for this data set? And I think, oh, I need to see what is my current structure of my data set. Where did I put my data? That is where my data is. Okay, good. Okay, so I do want to samples, and I want to do my square. This is now, instead of providing a pairwise distance matrix, I'm providing a point cloud. Okay, but I need to specify format is point cloud. Okay. Uh-oh. Did I change the?
Get a typo in format.
Ah, thank you. Yeah, my keyboard is it's going through some process. I need to really have it fixed. Okay, so this is simple, right? I'm point cloud with 4 points in dimension 2. It has a value range. So what is this value range? This value range, this is really the length of the diagonal, right? Sorry, half the length, 1.4. This is the length of diagonal, okay? This is really like the longest edge you are going to have when you actually go through that filtration. And what it says is that in dimension 0, it again has, because there's 4 points, so there's 4 bars of dimension 0, right? Which talks about exact the time where the points merge with it. And not surprisingly, because, you know, I know exactly how to construct the point cloud. I know that at sort of, I mean, actually, this is not radius. This is actually diameter. At diameter 1, right, that the component are merged, okay? Because, you know, it's a square. And then what happened is at this, when at 1, when all 4 of them connect along the square, there's a tunnel that is being created. But then when the diagonal edge shows up, okay, that tunnel actually disappears. Why? Because actually when that diagonal shows up, because remember I said Ripser filtration. Rip's filtration is when all three ways shows up, or three edges of a triangle shows up, the triangle also shows up. So the moment this edge shows up at time 1.414, the triangle also shows up exactly at 1.414. What does that mean? That means that tunnel that is born at 1 get completely filled in. And in fact, in this case, when the diagonal shows up, 2 triangles shows up at the same time. So it fills the entire area. Does that make sense? Okay. So
Why
the
doesn't
next,
the-
yeah, go ahead.
So at the end, you're going to have 2 tunnels from the 2 triangles that were formed?
No, you only have 1 tunnel actually. If you look at here.
But when you join the diagonal, now you have 2 triangles?
Yes, you have 2 triangles shows up at the same time. So let's let me do another share. Let me share my other board. So okay. So what I want to do is, remember this square looks like this, right? So this is 0, 0. This is 1, 0, 1, 1, and 0, 1, okay? And now what happened is that that the filtration is at time 0, all 4 of them. When I say time, it also means, let's say it means a diameter, right? At diameter 0, all 4 of them shows up. And then think about those balls grow. And then at some point, at radius 1/2, oh, that's not a very good drawing. Let me redraw it. So this is, let's say D at diameter 0, this is how the space looks like. At diameter 1, which is radius 1/2, okay, this is where all the edges shows up. Okay, so this is when diameter is equal to 1. And this is also where a tunnel shows up, right? Remember now the ribs complex look like this, okay? Now at diameter 1.414, okay? This is your radius became so big that along the diagonal, right, the balls touch each other. But if you think about the ribs filtration, what happened is that also at this diameter, what I highlighted in yellow, for example, for the lower right corner of this yellow triangle, all its edges shows up. And by ribs filtration's definition, when all the edges show up, that triangle also shows up. So the corresponding triangle also shows up. Okay, it's correspondingly to the upper left part as well. In fact, if you want to really enforce it, there's also this one. But to destroy this tunnel, you really just need a pair of triangle. But in fact, you can have 4 of them, right? But the problem is now, not the problem really, is there's a tunnel showed up at diameter 1, but at diameter 1.414, because all the triangles kind of come in. And if you think about, the balls, they kind of cover the whole space, so that tunnel disappear. That's why you get this feature right here. Does that make sense?
Why don't the triangles show up as a feature?
So here's the thing. The triangle, what is triangle a feature, right? No, the triangle is not a feature. Remember, we care about tunnels. Component and tunnels. When the triangle, well, the problem is there's not, in this particular case, right? When the edge shows up, let's say if I just look at this edge that I have no triangle right now, if there's a delay for the pink triangle show up, if there's a delay, then there's an additional tunnel. But there's no delay because the moment that this edge shows up, right? I see what you mean is that when I have an edge shows up along the diagonal, I should have created another tunnel, right? But the problem is that tunnel is born at 1.414, but it also died at 1.414. So the persistence of that thing is 0. Okay, because it's born and die at the same time.
Okay. Mhm.
Does that make sense?
Yeah.
Okay. All right. So let's, if you're next to it, another thing you can do is you can actually run this. So I'm going to stop sharing. I'm going to share a different screen. Now you can run this by running the online version. Oh, where's my online link? Right here. Okay. So if you run this live and you say, okay, I'm going to provide a point cloud and I'm going to run it from dimension 0 to dimension 1 and up to distance, say 1.5. Well, let's make it 2, okay, for good measure. And now I'm going to choose a file. And we did square, okay? Okay, so it visualizes the barcode. Remember, I have been using sort of the, beginning ending kind of pair of values to represent the bar, but this is a visualization of it. There's 4 0-dimensional bar because they're corresponding to 4 component and 1 goes to forever. I mean, I set the parameter 2, so it's only draws here, but it didn't die, right? It goes to infinity. And then there are 3 of them, which all disappear at diameter 1. And now I have a loop that is born at 1 and dies at 1.4. Oh, at 1.414, okay? And takes 0.02 seconds, okay? Since we're here, let's just do another example, right? So if I do a cube, so this is cube. This is like 3-dimensional point cloud, right? Again, and what I'm doing here is I'm going to, well, actually my parameter, I have to reset my parameter. Point cloud, I'm going to do dimension 1 to 2 up to a distance. So it has to be 5 times 1.414. Let's say it's like 8, okay? And then I'm going to do the cube, okay? And that's what you see. Well, this one is kind of tiny. Well, there's no void. So again, not surprising, I have, in a cube, I have 8 points. So I would have 8 bars. 7 of them disappeared at exactly 5 because that's the diameter where they connect. And now what's interesting in dimension 1 is, of course, you have similarly, when a diagonal shows up, it kills off the tunnel. So if you see how many tunnels do I have for a cube, I have 5 tunnels. Okay. Can someone tell me why it's 5, not 6?
Because the 6th one, it can be represented as the sum of the other 5.
Yeah, exactly. Right. But another intuitive one, which sometimes if you want to convince yourself, is that if you take a cube that is made by those skeletons and you start filling each of the face by pairs of triangles, right? You start filling them. After you have filled 5 of them, what you're left with is a square bowl, right? So there's no more tunnel left. That's exactly another way to imagine what you just described. The mathematical reason of it is because the last tunnel can be expressed as a combination of other 5, right? So it's not an independent tunnel in a way, okay? So that's what's happening in a cube. And now since we're here, let's do also, let's just do the triangle. So I also have example, I said it's a triangle, right? This is very easy, 0, 0, 2, 0, 0, 1, right? This is how the triangle looks like. And because now I have this triangle that has different length information. So in this particular case, you see that, I don't have any tunnel features because in this particular case, there's no tunnel is because the time the edge shows up, the triangle shows up at the same time. So a sort of a loop is born and die at the same time. So it does not show up at that barcode. But again, this length is precisely when the vertices are connected, okay? So there is quite a bit of things you can do. And then this is just a quick demo, and you can run it through command line, or you can run it through the online interface. Okay. So that's what I want to say about Ripser. And of course, the challenge, what you want to do, right? The challenge is, now I have given you those examples. I would challenge you to see if I computed, if I compute by hand, is this going to give me the same sort of result as what Ripser gives me? But if you want to compute this by hand, remember your filtration of the simplices has to be constructed following the rule of the Rips filtration. So Rips complex filtration. Okay. So how do you do this by hand? You start with the points, and you kind of, as you increase the radius of the ball, you want to think about when does an edge shows up in my filtration and when does a triangle shows up in my filtration. And you can also do this computation by hand by doing either a Rips filtration, which is what Ripser is based upon, or a check filtration. Remember check complex. A triangle only shows up when there's three-way intersection. So if you do checks filtration, you're going to get a different result with this point cloud. Okay. All right, so that's the example, and so on. And what I show you on the screen is what's going to look like if you actually just run it on your, from the command line. Okay. So we just went through example, and now I'm going to move on to what I want to cover, and let's see how far we can cover today. All right.
I have a really quick question. I just want to make sure. So for instance, with the square example, what happens right when the hole, I forgot what word it is, when the hole disappears is actually 4 triangles all get created simultaneously, not just 2, right?
Yeah, there's actually 4. Yeah.
Okay. All right. Then
but the thing is that to destroy that loop, you don't need the 4 of them, right?
Yeah.
So if you want to destroy it, it actually shows up quite quickly. So yeah. Okay. All right. So now we know how to compute it using a tool, Ripser. Now we also know how to compute it by hand. I like to come back to revisit our framework. So what is a TDA pipeline, right? If I have a pipeline where I have some data, and my data can take different forms. The data that we just saw is the point cloud data. You can provide a pairwise distances into Ripser. It will construct a Rips filtration for it. Or it can be other form of data. For example, it can be images or it can be graphs, okay? And what you want to do is to what we say construct a filtration. So what is a filtration? A filtration is basically you're constructing a simplicial complex one at a time, where you are always adding element to my simplicial complex, and where it satisfies the condition where each time I add a simplex, all its faces has already been there. So each time I add something, it always remains as a simplicial complex. And then once you have the simplicial complex, you kind of construct this boundary matrix as we did before, which is each column is a simplex and each row is also the simplex in the same order. I look at the boundary matrix and then do this kind of column reduction by maintaining the lowest unique ones. And then you can read off the barcode from it. But once you have the barcode, what do, right? You can do downstream analysis now. You can take this barcode and treat this barcode as a feature vector, and you can use that for things like classification, or you can do visualization and so on, okay? So that is a general pipeline. So I want to mention briefly, in this case, sorry, I didn't want to use this color. I want to do, what if my input is a graph? Okay, it's no longer a point cloud. How do I construct a filtration? Okay, so that's, I just want to give you one flavor of it. So let's say this is my graph, okay? My graph looks on the left corner. This is my graph, okay? And it has a bunch of vertices, a bunch of edges. Okay, so what is a filtration? My filtration will start by just having the vertices. Okay, so I would say, what is my filtration? My filtration is at time 0, only my vertices, not the edges, okay? only my vertices shows up. Okay, that is my time 0 simplicial complex. At the next time step, what I do is I'm going to add the 2 clique of this graph. What is a 2 clique? A clique is one subgraph that connects everybody in my set of vertices. I mean, 2 clique is one that connect all pairs from my graph. So what are the 2 cliques in my graph? Those are the edges of my graph. So in my second step, I add all the edges, right? They are highlighted in yellow. Those are edges from my graph. They are also the 2 clique. So that is my second step of building this filtration. So first step, all the vertices. Second step, all the edges of my graph. Third step is I want to add what we call 3 clique. 3 clique are triangles formed by pairwise edges from my graph. Remember, my graph data is just a graph, but I'm constructing a simplicial complex, right? So in this case, what I'm going to add is going to add all the 3 clique of a graph. So a 3 clique graph are all the possible triangles that is formed by the edges. And in this case, there is actually, I'm going to use green also. Like, for example, on the upper left corner, there's actually 4 triangles you add. So this is one, this is another one, and this one, and this one, okay? And of course, you add all the remaining triangles that is possibly formulated. So that's step 3, right? I'm adding all the 3 clique. And now 4 clique. What is a 4 clique? A 4 clique is usually you have 4 vertices and you have all pairwise connections. And that red spot is where my 4 clique shows up. But in my simplicial complex term, that is corresponding to a tetrahedra. Okay. So the step 1, I start with vertices in my graph. Step 2, I add the edges of my graph. Step 3, I created new triangle with a particular rule. And step 4, I added a tetrahedra based on my rule. Okay. So this is actually called the clique complex of a graph. So now you have built this filtration. You can do the exactly same thing as I did before, right? My filtration is where each of the simplices show up, and I can construct a boundary matrix, and I can do my boundary matrix reduction, and this then gives me a barcode for my graph, okay? And that becomes my topological signature of this graph, okay? So let's see what this example looks like. You can also looking at essentially the persistent homology of this, right? I remember my filtration has 4 steps, but what I'm doing here is I'm saying that at each step, I'm telling you what is the homology of that step. So for example, in the first step, it's just all the points, right? So I'm asking you, remember here, I'm looking at beta 0, beta 1, and beta 2. Beta 0 is tell me at this point, how many components are there? Can someone tell me how many components are there?
It's just all the points, so 9.
Yeah, so it's 9, right? And then there's nothing else. There's no tunnel, there's no void. So that's 9, okay? Now, if I added, okay, if I added all the edges to connect those points, okay, from the original graph, right, all the 2 cliques. Now, how many components are there?
Just 1, because they're all connected.
Yep. And how many loops are there?
I want to say 2.
Okay, it's actually 5.
Okay.
Because exactly what happened here.
Yeah.
So remember, there's no triangles, right? So there is at least 2 loops, and what you see. There is additional loop once I added that edge. But there's not 6 loops because the last one can be combined as a linear combination of other 3. Okay. So again, the way to convince yourself there's only 3 loops instead of 4 loops is thinking about this, treating this as a tetrahedra, okay? And you start filling the faces. So for example, I'm going to fill the back end of the yellow face. I'm going to fill the side end of this pink face. And now I'm going to fill what? Maybe this face right here. Now, thinking about this, I have a tetrahedra. I have 3 faces filled. What do you get? It's a bowl, right? You no longer have additional tunnel. So you only have 3 tunnels in that area, plus this tunnel and this tunnel. Well, actually, I shouldn't do that. I should just, this is a tunnel. Okay, so that's why there's 5 tunnels. And now next stage, when I add all the triangles in my filtration, I know that my tunnel all disappear, right? I have 1 component still, but the interesting part is now I have 1 void. Why? Because I have not put in a tetrahedra. This particular area where these 4 vertices form, I put all its faces, but I did not fill it in. So it's kind of hollow in the middle. That's why there's a void, okay? And then that void gets disappeared when I actually put a solid tetrahedra in there, okay? So that's why at this stage, I have 1 component and then no tunnels and no void, okay? What is my barcode looks like, right? I told you, in some sense, persistent homology is looking at the evolution of component over time, evolution of tunnels over time, birth and death of those. And what I just did is I'm looking at the homology of the space at a particular parameter. So what is a barcode? I know that I'm going to have a bunch of, so I'm just going to do it. Okay, this is time. I know I have at least 9. I will have 9 components all born at time 0, okay? And let's say at this time, let's call this time 1, and this is time 2. It's not the best way, but let's say this is that. So at time 1, time 2, time 3, time 3, okay? At time 1, or among 9 of them, 8 of them disappeared. So you have 1, 2, 3, 4, 5, 6, 7, 8. And then you have 1 that goes to infinity because that component never dies, right? And now, remember at time 2, that's where a bunch of loops is born. So I'm going to use a different color. And actually what I really want to do is I want to do up on top of here. So just excuse my abusing of my space, but I want to say that, there's 5, 4, 5. There's 5 of them that is all born at time 2 and all died at time 3, right? When the triangle comes in, all those loops disappeared, okay? So that's the second sort of type of bar. And the third bar is at exactly time 3, I have a void that is born. Let me use green. So the green is born and it disappeared at time 4. So in a way, my barcode, right? Excuse. Copy. This is how my barcode looks like. Okay.
I think
so
the barcode. I'm sorry. I think the barcodes for dimension 1 and 2 should be shifted by.
Oh, you're right. Actually, perfect. Yes. Yes. I just realized it. Why is there a gap? Okay, so it should be this. Sorry. Oh. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. This is what it should look like. Okay. So I'm going to delete this so it doesn't confuse people. So that is become the signature of this graph, okay? And you can imagine I have a different graph and, depends on how that graph is constructed, using this filtration, I get a different barcode. And I can compare now the graph by compare their barcode, right? Okay. But one thing I have to be careful is that going from my graph to this barcode is in a way is what I would call a lossy process, meaning that you lose information during that process. Okay, so it's not a complete descriptor. What that means is that it's also possible that you are going to have two different graphs, but then it's going to give you the same barcode. Okay, which means that even though I can compare them, if the barcode is the same, does not imply the underlying graph is the same. Okay, does that make sense? So in a way that if you want to do that for, in some sense, classification, you know that if their bar is different, you know the underlying space is different. But if the bar is the same, it does not imply the space is the same. Okay, so that's what you want to keep in mind. Okay, that's exactly what I just do. Okay, so, you know, 0-dimensional bar, 1-dimensional bar, 2-dimensional bar. Okay, so now, well, now I have 3 minutes to finish actually lecture 10, but that's okay. We'll kind of flow over the next lecture. My next lecture is a short lecture that we're going to talk about manifold. But let's give you a flavor of what is a mathematical formulation now. Well, we know how to do it. We know how to compute it. What are we doing in terms of what I call filtration? Okay. So one way to construct a filtration is my K is a simplicial complex, okay? A collection of vertices, edges, and triangles. And then there's some real values on it, okay? And translating to our early example, this is exactly the labeling, except I just happen to choose integers, okay? So what does this number do is I can use this number to derive an ordering of when my simplex is going to show up in my simplicial complex. The requirement I need for this function is basically what I mean monotonic. It has to be monotonic with respect to the following condition. If sigma is a phase of tau, then the function on sigma has to be smaller or equal to the function of tau. What does this really mean? This just means that the phases of my simplex have to show up before the simplex itself. So for a triangle to show up, all its edges have to show up earlier than it, right? This is really what monotonicity is requiring, is that at any step in time, when I add a simplex, I'm always having a simplicial complex. If that is violated, if this condition is violated, you might be adding a triangle when not all its edges is in place. Why is this necessary? Because if I say my filtration goes, oh, I have a vertex, I have another vertex, I have another vertex. That's 1, 2, 3, and then 1, 2, 3. And then my next thing is I just added this triangle without adding the edges. Okay, so the edges hadn't show up before the triangle, but I add the triangle. What's happening is that if I look at the boundary matrix defined at this moment, it's not well defined because all the boundary is not even there, right? So you can't even proceed with your algorithm. Okay, but that's just one small justification. You need to have a proper simplicial complex to have a proper boundary matrix at that time. Okay. All right, so the next thing is I'm going to define what's called sublevel set. Sublevel set is basically all the simplices that has a function value smaller or equal to a particular thing, right? A particular value. It's just, you know, look at all the simplices whose function value is below a threshold. And now imagine all the simplices. Let's say this is just my simple simplicial complex. 3 edges, 3 triangle, 1 triangle, and 3 vertices. And it's going to have what? 7 function value, assuming all the function value are unique. Then the filtration is a sequence of simplicial complex that is going from left to right, and it's sort of as inclusion relation, right? So, you know, K0 is always a subset of K1 is always a subset of K2 and so on and so forth, assuming my values, my 0 to my A0, well, A0 is usually infinity, okay? But A1 to AN are all the different function values attached to my simplices in my simplicial complex. And then what I do is I build a filtration based on this ordering. And that is a filtration I've been talking about. They are sequence of simplicial complexes where the difference, if I say difference, right? If I use in this symbol, this is where the new simplex is added in this particular step. Okay, that's That's a mathematical formulation. And then once you have the sequence of simplicial complex exactly here, this is my K. Well, actually my K0 is always empty. So K0 is here, which is empty set. And this is my K1, this is K2, this is K3, this is K4. Right? Those are my simplicial complex over my filtration. And then for this, it gives to a sequence of homology groups. So you basically compute, let's say P is equal to 0, P is equal to 1. This is a dimension of my homology. 0 is component, 1 is loops. So I'm looking at how the homology is mapped from one to another. And that's what persistent homology is doing. But at a particular fixed time, let's say at time 1, this piece here, I'm just looking at the homology of the space at this point. Okay. Right, so that's exactly what we did. We look at the homology right here, homology right here, homology right. Oh, actually, this table is better. Homology, 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 homology. Okay, but then persistent homology is looking at the evolution of those homology classes. Right, for example, at K2, there is 5 loops or 5 tunnels, and then at K3, those 5 tunnels disappeared. That's why my persistent homology have this bar, is because I'm tracking at time 2, how many homology are there, and at time 3, how many homology are there, and how do they map into one another, right? That's exactly what this sequence looks like. So in the next lecture, I'm just going to go over, defining this filtration, and we can go a little bit more into the detail of the algorithm. And my recommendation is read this chapter from the textbook. It describes a bit more over the matrix operation of the reduction algorithm we just did. And then in the book, there's also the pseudocode of how it's done. Okay, so that's that. Any questions?
Yeah, I was just a little bit confused as to how the edges were drawn when you were generating the 2-click.
Oh yeah, so first of all, let's just look at the click definition, right? So 2-click is the edges coming from the graph. 3-click is 3 edges. Okay, but my click filtration, right? The click filtration, remember it's a filtration. So I want to build a simplicial complex out of my data, which is graph. So my first step is all the vertices of the graph form the vertices of my simplicial complex. The second step is I'm saying that all the edges of my graph form the edges in my simplicial complex. So what I'm saying is that I am treating my graph as my data, okay? So when somebody give me a graph, it's vertices and edges, right? But I would like to build a filtration of simplicial complexes out of that data. That's why I want to kind of build a rule of how do I build not only vertices and edges, but triangles and tetrahedras out of this data potentially. So I'm creating a rule, meaning that I'm going to start by building my simplicial complex by saying that my vertices of my simplicial complex are the vertices from the graph, and my edges are the edges from the original graph. And then I'm going to add triangles whenever there's a 3-way connection from my original graph, and I'm going to add a tetrahedra whenever there's a 4-way pairwise connection from the original graph. So this is a notion you might not be familiar with, is that when people look for a clique in a graph, you're looking for a subset. Let's say if I'm looking for a 4-clique, I'm looking for a subgraph of the original graph such that there's a pairwise connection of a subgraph size 4, that there's a pairwise connection. That's called a 4-clique. So the rule I'm using is whenever there is a 4-clique in the original graph, I'm going to add a tetrahedra into my simplicial complex. Whenever there's a 2-clique in my original graph, which is basic, a 2-clique is an edge. Whenever there's an edge in my original graph, I'm going to use the same edge in my simplicial complex. That's a rule. Is that making sense?
Yep, that makes sense. Thank you.
Okay, good. So, but I have to be careful. With the graph data, there's different ways to model your data, okay? What I just said here is a Clique complex definition, which build a particular filtration. There's other ways to build a filtration. For example, since we're on this language here, one way is, let's say, my pen just gave up. So my pen is just like, okay, end of the class. So one way to map a graph into another type of filtration is you can treat the graph as a metric space, meaning that let's say there's some, for every single point, a pair of points in the graph, their distance between them is going to be their shortest path in the graph. Okay, so for example, in this upper example, let's say all the edges has weight 1. Then the distance between node 1 and 2 is 1. The distance between node 1 and 5 is 2, because the shortest path goes through 2 edges. The distance between node 1 and 9 is 4, because the shortest path goes through 4 edges, and each edge has a weight of 1. So now you have converted this graph into a point cloud by providing their pairwise distances, right? Because every single vertex between the graph become a node in that metric space, right? It become a point in that space. And then the shortest path between any two pair become their distance. So now if you're using Ripser to compute the persistent homology, you can just provide the pairwise distances into Ripser, and Ripser will give you a signature of your graph. But that's a different way of mapping your graph data to be a filtration, because now you are mapping the graph data to a point cloud or metric space to be more precise, but you are looking at the pairwise distances using shortest path distance. And then if you do that, you're going to get a complete different type of signature of this graph. Okay, so one interesting thing about thinking about how to use persistent homology for your data analysis tasks is there are very different ways to model your original data into a filtration and into the framework of persistent homology. And for example, in graph, you can use a Clique filtration, or you can do the shortest path filtration as what I just described, and they will give you very different signature. Okay. Any other questions? All right.
Just a quick clarification on Ripser program. So the parameter is not the radius around each point, but it is the distance. Yeah. Okay.
Yeah. So it's all boiled down to a scaling issue, right? If my filtration parameter is using radius, then all my bars is going to be like half the length of what Ripser gave you. But it's if you think about it, is you take all the bars, you uniformly rescale it. Right, that's what's happening. Yeah, but Ripser is actually like the parameter as we showed for the square example is actually the parameter they are looking at is diameter, not the radius. I like to use radius because I'm thinking about like the radius of the the radius of the ball versus diameter of the ball.
Right. Yeah.
Yeah.
Thank you.
Okay. All right. So I'm going to stop streaming, and if you